Hey guys, welcome to today's video on enthalpy of reaction. So you remember in an earlier video we talked about the fact that matter can undergo either physical changes or chemical changes, and whichever kind it is, there is always an accompanying energy change. And then in that earlier video we looked at a dissolving physical change and we calculated the enthalpy of solution. So today we're going to do a similar type of thing, but we're going to end up with an enthalpy of reaction because the change we're going to look at is a chemical reaction. It's the reaction between magnesium metal and hydrochloric acid. So let's write down some data. We have a beaker and we're going to add to the beaker 200 milliliters of 2 molar hydrochloric acid. We're going to record its initial temperature, that's room temperature, and then we're going to add some magnesium to it. Now, it's going to be important that we know the mass of this reactant. 200 milliliters, when we put it on the balance, has a mass of 203.41 grams, and the piece of magnesium we're going to use has a mass of 2.43 grams. All right, so I'm going to show you just a quick video of the actual reaction so you can see what that's like. And let's spot.
I just wanted to watch really closely what happens.
So the magnesium went in to the acid, and you can see right away the production of the hydrogen gas.
So I don't know how clearly you can see that, but there is actually steam coming off this, and if I feel it, it's really quite warm. It's bubbling very vigorously. You can hear it.
Definitely an exothermic process. She said you can
feel just bring it close so you can see there is a tiny bit
and there's a little piece
of magnesium ribbon left on the side there. If I just tip it so hydrochloric acid gets in contact with the magnesium ribbon, you should hopefully be able to see more bubbling. And the magnesium ribbon in this second tube has actually completely disappeared.
Okay, so that's important. She ran the reaction until the magnesium was completely gone. And then the final temperature was recorded, and the temperature went up quite a bit. So final temperature is 76.12 degrees Celsius, which means our temperature change is 53.62 degrees Celsius. And let's make a note, because the temperature went up, the surroundings got hotter. This is another exothermic process. Okay, so you'll recall that when we were doing enthalpy of solution, we used the Q equation, the MCAT equation, taking all of our measurements of the surroundings. So our MCAT equation tells us that the heat energy for the process is equal to the mass times the specific heat capacity times the delta T. And remember, guys, that the temperature that we measure in a calorimetry experiment, the thermometer can only measure the surroundings. So what we're putting in here is all the information about the surroundings. Everything in the cup is what we want to add together for mass of the surroundings. So it's the hydrochloric acid reactant that we put in first, as well as the magnesium reactant. And then the constant, once again, we're going to fudge a little bit and assume that it's okay to use the specific heat capacity of water. So when we plug in our values, the total mass of everybody in the cup, the specific heat capacity, and the temperature change, then we get a value for Q, the heat energy, 46,179 joules. Now, that Q is the heat energy that was involved in this particular trial. with these amounts of reactants. But we would like to use something that's more general. So we would like to change this very specific Q heat energy to something more general, the enthalpy change of the reaction. And to do that, we want to take our heat energy, convert it into kilojoules. Remember, we divide by 1,000. And then we'll divide that by the moles. But here's my question. Moles of what? When we were doing enthalpy of solution the other day, it was really easy to see, well, since this was a dissolving process of a solute, we used moles of solute in the denominator. In an enthalpy of reaction, if you have more than one reactant, as we do here, how do you know which one to use? Well, I want to propose to you that you want to use the moles of the limiting reactant. Now, that may be intuitively evident to you because it was the magnesium that got used up first. And in fact, the magnesium is the limiting reactant. But let's just do the math to prove that to ourselves. So using the periodic table, here's my mass of the magnesium reactant, molar mass from the periodic table. So this amount is 1/10 mole. Now, to get the moles of HCl, be careful here, guys. You cannot take this mass and use the periodic table molar mass of HCl to convert. The reason is this mass is not exclusively HCl. Some of this mass is HCl molecules, but it's all dissolved in water, so a good portion of this mass is water, which isn't a reactant. It's just the vehicle, the medium that holds everything together. So to figure out how many moles of HCl we used, we have to use the volume and the molarity to figure that out. You'll remember that from our solution unit. 200 milliliters changed into liters, multiplied by 2 molar, moles per liter, set it up so that liters divide out. So in this particular reaction, we had 1/10 of a mole of magnesium and 4/10 mole of hydrochloric acid, HCl molecules. So here's 1/10 and 4/10. And our balanced equation says that for every 1 magnesium, you're going to use up 2 HCl's. If all this magnesium is consumed, 2 HCl's will be consumed. And these 2 down here are going to remain left over. So some of this is used and some is reactant in excess. In fact, the portion of HCl that will be used for this amount of magnesium would be 0.2 moles HCl. Alrighty, so having said that, now we're going to take our heat energy once we've divided it by 1,000 so that it's expressed in kilojoules, and we're going to divide it by the moles of limiting reactant. And when I divide, I get 462. Now, careful here. We are not done yet. Simply dividing is not the final story. There are 2 really important things to add here. One is the sign. So heat of reaction, enthalpy change of reaction, and enthalpy change of solution always comes with a sign. We said this was an exothermic process again, just like our enthalpy of solution example was. And exothermic processes are always accompanied by a negative sign. The reaction system is decreasing in its enthalpy, so the enthalpy change is negative. Now, the next thing I want to show you is the unit. It looks like our unit should be kilojoules per mole of the limiting reactant. But in fact, the unit has to be able to apply to any reactant here. So what we're going to do is add one more piece. We're going to say in this equation, there is 1 mole of magnesium in 1 mole reaction. That mole reaction is kind of a funny unit, and it's actually fairly new. Your textbook doesn't even use it, but we are going to use it. Moles magnesium divide out. So negative 462 kilojoules per mole reaction is the value of the enthalpy of reaction. Let me just show you how that would work if we had based it on the HCl. So if we did that very same experiment and we took our Q, changed into kilojoules, and we said, okay, and that happened when we used 0.2 moles of HCl. Then we go to our balanced equation and we say, and oh yeah, in this reaction, there are 2 moles of HCl in a mole reaction. Moles HCl divides out. Now when you multiply through and divide, your answer is exactly the same. Negative, because exothermic, 462 kilojoules per mole reaction. This is saying that this many kilojoules are released for every 1 mole of magnesium, or this many moles are released per every 2 moles of HCl. Okay, guys, I hope that was helpful.